last time we learned the method of images. And then as a non-trivial example, we learned about the sphere, conducting sphere, and the point charge Q case. And then here, the conducting sphere is grounded, which means like this thing means it's grounded, which means V equals 0. Okay, so just V is same as the V at the infinity. And then we learned that if we place an immediate charge Q prime here, like, and then if you write the potential due to the original charge and the immediate charge, and you write the equation for you know, like both charges, you realize that if this, you know, the position H and the charge amount Q prime satisfies these two equations, you know, the potential becomes 0 at the conductor surface. And then, as I said earlier last time, the two conditions will be just determined by the condition, like making the potential here and there to be 0, right? And that already becomes two conditions. But if that the H and Q prime satisfy this condition, then on all conducting surface, like all the spherical surface, the potential becomes 0 and it's equipotential. So it's problem solved. So here, my question is that, like, if we make a little change in this problem, so let's assume that this charge, I mean, this sphere was not grounded. And we don't know the potential of this sphere. But instead, let's assume that this sphere is not connected to anything, which means how do you translate this condition? Like, let's say if we have a sphere, uncharged sphere, and then we did not connect this sphere to anything, not connect to ground or not connect to anything, then which condition should be satisfied? Like if the sphere is not connected and then initially it's uncharged, then which condition should be satisfied? Can anyone answer this? So if this was grounded, that means the sphere is equipotential and V is 0, right? And then what if, what condition should be satisfied in this case? Sphere is disconnected. E inside the sphere is 0. Well, that's anyway true. Like Lee Chung-pil said, the electric field inside the sphere is 0. This is nice, but anyway, this is conducting sphere, so it should be 0. Laplacian V is 0. That is also true because E is anyway 0, right? So Laplacian V is also 0. So that is also satisfied, but that's kind of was satisfied before too. So if I just tell you the answer, because we have a limited time today, if the sphere was uncharged, then what should be conserved is the total charge amount. Okay, because charges cannot get in or get out from the sphere. So the net charge must be 0 anyway, right? Because it's initially Q was 0. After this everything, net Q must be 0 anyway. But from this example, what we know was that if you place Q prime here at this position, like the amount is minus A over BQ, then this surface becomes equipotential. Okay, and if we have only one immediate charge, that with this charge amount, then the net charge of the sphere is non-zero, right? Non-zero, but minus a divided by q. So how should we solve this problem? Like if we are asked the same question, then what do you think we should do? Do you have any idea to put more immediate charges to solve this problem? Well, in any case, the surface of the conductor must be equipotential, right? That is kind of rule number one. So, and then you may realize that there's only one place that you can freely put anything without changing the property of this equipotential surface, without perturbing the equipotential property. Where is the position? Can anyone answer? If we, right, exactly. So there are many correct answers. We can place another initial charge, immediate charge at the center, right? Even though, so we can put anything at the center without changing the equipotential property of this. Of course, the absolute potential will be changed, right? As we put the charge at the center, but it wouldn't, perturb the equipotential property. So it's the spherical surface would be still equipotential, right? So as Park Se-hoon said, and many other people said, we can put minus q prime at the origin. Then the net charge of the sphere becomes 0, and then everything's happy. Boundary condition is now satisfied again, right? So this is how you treat this type of a problem. Okay, so type in your question if you have any. I'll just go on. The next thing I want to discuss is another thing that can be even one step more complicated from this question, this problem, which is this. Okay, so what I'm gonna say here is, instead of having point charge q, we have a sphere with net charge q. Okay, and we have another sphere with the same radius that is grounded. So one question is, compared to the case with point charge with the same sphere. So let's say this is case 1 and this is case 2. In which case the force between two spheres becomes stronger? In which case the force exerted on this sphere will be stronger? Can anyone answer this? Case 1 or case 2? Okay, so in the meantime, I will address. So if you have any answer, just type in as Kang Yong did. And Park Jun asks, so even when sphere is ungrounded, we need to maintain the boundary condition that V at surface. No, Park Jun, that's not true. So we need to satisfy the condition that V is constant at the conducting surface. It's not 0, right? It's not 0 at the surface. So V must be constant at the surface so that there's no current flows. Okay. And then Kang Yoon said in this problem, said case 1, it's going to be stronger. Lee Chung-pil said, I think it'll be the same, case 1 and 2. Who do you think is correct? Which one is correct? Case 1 or case 2, they're the same. What's the force? So of course, we are assuming the center of the distance, center to center distance here, and the point charge to center distance are exactly same. So if I just tell you the answer, Gangyung is correct. Case 1 feels the stronger force. The reason is because if you have net charge Q here, the discharge Q is actually distributed on the surface of the sphere, and then the way it's distributed is not like the way it's balanced, so that its net kind of center of charge is at the origin. The way it's distributed is actually leaning toward to the other charge. So if you kind of think about the center of charge, it's somewhere here, a little bit closer to the other sphere. So the force between these two charges is stronger for case 1 compared to case 2. Okay, so let's think about how to deal with this problem. So the way we deal with this problem is a little bit complicated. So what we are gonna do, so the typical way we do this problem is using series solution. So we have charge Q. We can just begin with assuming the charge Q at the center. Okay, then the sphere 1 becomes equipotential, right? Sphere 1 is heavy now. And then due to this charge 1, we can think of image charge Q prime here, right? Which is, the charge amount and the position. And then sphere 2 is heavy. But due to this image charge, sphere 1 becomes unhappy, right? So we have image charge of image charge. So we have Q double prime, which is an image charge of a Q prime, right? Now sphere 1 is happy, but then sphere 2 becomes unhappy. So we need image charge of Q double prime, so which we call Q triple prime. And this process goes on forever. Okay, so we need, by putting infinite number of image charges, we can achieve the solution of this system. And then if you're worrying about the convergence, you don't need to worry, because the amount of charge Q prime is minus B over A over B, and then as long as B is larger than A, which is always the case, the amount of Q decreases like rapidly. So it kind of forms a converging series. So you don't need to worry too much about the convergence. Okay, and finally, what I want to cover is applying the same technique, the method of images, to not to the conductor case, but to the dielectric case, dielectric interface. So here, as a final step, we deal with charge Q at height h from the surface. But here the difference is that this surface is not a conducting surface. Instead you have a epsilon 1 and epsilon 2, like dielectric surface. And how to deal with it? Like if it's a dielectric surface, boundary condition changes. The boundary condition is not like electric field, something like this, right? It's more complicated. It's about the tangential field of electric field and normal field of a D field. And then if there's no external charge applied to the system, both of these must be continuous, right? So how to deal with it? the problem itself is the same. Like in order to solve, so we divide the region into two, upper half, lower half. In order to solve upper half, we need to include the original charge and the charge at the mirror position, right? And then assuming that the electric potential at region 1 is the electric potential due to these two charges. And then we do the similar thing too, like for the epsilon 2, in the region 2, we put an immediate charge at the original charge position. And then assuming that the electric potential at region 2 is due to the original charge and the immediate charge. And then we apply the boundary condition, D1 and E1, D2 and E2, and we get equations, right? Two equations. And then we have two unknowns, Q1 prime, like Q prime and Q double prime. And we solve it and we get the solution. So again, like if you look at here, in order to solve the upper half, we put an immediate charge at 0, 0, minus h at this position, the mirror position. And assuming the potential in the upper plate, upper half, is the potential due to the original charge plus the immediate charge Q prime. And then in the medium 2, the lower half plane, we place the immediate charge at the same position of the original charge. And then we call the sum of the original charge and immediate charge to be Q double prime. Because they're on the same position, we just call it as Q double prime. If we do that, the potential in medium 2 is just Q double prime, right? And then we have boundary conditions, two boundary conditions. The surface tangential E field must be continuous. Surface normal D field must be continuous. And then how can we obtain D and E field? Well, we can, of course, take a gradient. Negative gradient of V gives you the potential electric field. And once you get the electric field, it's just you can apply the boundary condition. And then once you apply the boundary condition, you know how much of the immediate charge amount. How much was the immediate charge amount? And Kang Yung asks, what's the difference between Q and Q double prime? Okay, so yeah, so the first one, I guess it's easy to understand, like solving this part, right? Like a upper half plane, and then putting Q prime. So that's easy. But like solving here was like a different problem we never encountered before, because in this region, this was originally like inside the conductor, so E field was 0, but here it's not. So to solve this problem, and then another thing you notice is that like we have, so let's think about the actual situation. The actual situation, you have Q, and then because you have a boundary between two dielectrics, you must have some sort of surface charges at the interface, like surface bound charges, right, due to this guy. And then if you want to calculate the electric field or potential in the bottom region, bottom half, you need to take into account the effect due to the original charge plus this distribution, right? And then this distribution can be considered as effectively as a new charge at the original position, Q. So instead of dealing with this distribution, what we do is we assume that we have different charge amount is located at the original position. And similar thing applies to the other case too. I hope that answers your question.